Okay, I want to thank all the organizers for giving me this opportunity of explaining you a little bit the work that I've done and the spirit of the work that I've done in this postdoc, but also in the past years in physics. And as you can see from the title, it concerns universal system and effective field theories. Or a little bit of disclaimer here. I gave a similar talk a couple of weeks ago, and I expect that there will be some overlap in the people that are following this talk. And this has, I would say, two outcomes. The first one is that I realized how much more difficult it is to prepare a talk for the online presentation, and instead of having a talk in person, but I hope to see you in person soon. And the second thing is that I wanted to do something different. So for the people that overlapped, I changed slightly this talk. So the first thing is that I changed the picture in the title. So it's a completely different talk. And the second thing is that I'm going to talk more about hypernuclei this time. So I want to give you a little roadmap about the talk that I'm going to give today. Usually I don't do that, but since we are going to touch many different arguments and I want to be as clear as possible, I don't want you to get lost. So the first part will be more a theoretical introduction about contact theories, universality, and how we can interpret these two things together using effective field theories. While in the second part of the talk, I'm going to talk about hypernuclei and nuclear physics as an example of a system close to universality. But of course, universality is something that is much broader, so you can apply on different systems, as you can see on this drawing that has been made for the occasion. So before going to the systems, okay, the first part will be in common with the last talk. So if there are other people that follow my talk before, I will wake up you when there are new things. But the first part is more about understanding what is the concept of the work that I'm doing and why I'm doing this kind of work and why I'm studying this kind of physics. So thinking about how to make this talk, I found out that there are at least 3 different reasons why one want to study theoretical nuclear physics. One of them is to try to get the most precise description of nuclear observables such that you can compare it with experiments up to the best digit you can arrive with your numerical methods. Or alternatively, you want to try to support the experiment itself. For example, try to calculate some observable that has not been seen yet, but can be useful for future experiments. And usually making calculation is much cheaper than creating an experiment, so you can really create something that then can be experimented in a further and more expensive environment. And finally, there are people that like to understand the real mechanics that is behind emergent effects in nuclear physics or many-body physics. And in this case, you try to understand why some kind of effect happen in physics. And for theoreticians, this means that you have an interaction, for example, and you are able to reproduce an interaction and know what are the properties of an interaction that creates such an effect, such that you know why this effect happened. So in this talk, I'm not going to talk about precise description. I will focus on the first two, so supporting experiments and the mechanism of nuclear properties. Of course, this is just a personal opinion. There might be many other motivations why one want to do theoretical nuclear physics a part of, well, theoretical nuclear physics is cool. So if there is something that's drawing you here and is not here, well, this is just my opinion. So without further chit-chatting, let me talk to you about a little bit of the idea of universality. So universality is a very simple concept, which is as hard to, as simple to be understood, as hard to be really described mathematically. Universality means that there is a group of systems that, despite having a different microscopical description or different scale of energy and momentum or sizes, share an ensemble of common physical properties. Those common physical properties can be few body properties as scattering observables. They can be many body observables, critical exponent, or the same kind of states. The point is that if you have this kind of systems that have the same qualitative behavior, you expect to have a similar theory that describe all of these systems, despite them to be in nuclear physics, atomic physics, or hadronic physics, or any other system at universality. So you can describe them with similar theories. And to give you an example of universality, I want to talk to you about unitarity, or the unitary limit. This is the kind of universality that I'm going to use the most during this talk. So unitarity is the kind of universality classes, a universality system, in which the two-body system in this kind of physics is such that the two-body system has a finite range, but the interaction between the particle happen to have to be at very short range. So the particle interact only when they contact each other, but nevertheless, the two-body system and also the few-body system have a finite size, meaning that the size of the two-body system is much larger, in principle, infinitely larger than the range of the interaction. Of course, this is only possible in quantum mechanics. This is a pure quantum mechanical effect, but this is something that relates only the two-body system, and it's not important which kind of particle you have, as long as the particle have this universal property. Now, if you want to understand this more in a mathematical or in a more theoretical, we say, a way you have to recall what is the effective range expansion, which is the expansion of the phase shift of a two-body scattering problem. And this expansion has is an expansion in momentum, and you have the scattering length is 0, the effective range is 0, and all the rest of the scattering parameters. And you are in the unitarity limit when the scattering length goes to infinity and the effective range goes to 0. Essentially, the scattering length becomes much larger than the effective range and much larger than all the rest of the scattering parameters. Now you can say, well, but this is just an academical concept. This is something goes to infinity and to 0. You will never have physical system really with an infinite scattering length and 0 effective range. And well, you are correct. There are no infinite scattering length and 0 effective range, properly speaking, in physics, but there are many systems, or kind of few systems, that are close to the unitary limit. And here I have, for example, some example of them. If I give you some bibliography here, or some examples and some papers. And you can find system close to the unitarity limit in atomic physics, for example, in which using Feshbach resonances, you can really fine-tune your scattering length to be a very large value. But you have also nuclear physics in which, for example, the neutron-proton interaction has a scattering length of roughly 5.5 Fermi. The effective range is 1.7, so it's not much smaller. But for example, neutron-neutron is even better because you have a scattering length of -20, -18, -23, depending on the channel. And the effective range of 2.7. So you have one order of magnitude between the scattering length and the effective range. So nuclear physics and atomic physics are not really at unitarity, but they are very close to it. And there are instances in lattice nuclei, hypernuclei, and hadronic physics. Today I'm going to talk about nuclear physics and hypernuclei. One of the effects of this universality class, or this way of defining universality in the two-body, is what happened in the three-body. And this is very peculiar. I cannot go really in the detail, also because this will take a lot of time. But essentially what happened when you have a system at unitarity, so with a very small range of the interaction and very large scattering length, is that when you go to the three-body system, you cannot define theoretically the three-body system, meaning that the three-body system have what is called the Thomas collapse, which means that the three-body energy collapses, goes to -infinity when the range of the interaction goes to 0. And for this, you cannot really create, just with the assumption of unitarity, a three-body system and consequently a four-body system and a five-body system in this kind of universality class. You have also to fix the size of the three-body. And doing that, you are creating a new scale because you have to decide which is really the size and the energy of your three-body system. And this is usually done, for example, well, it can be done with a finite range or, for example, using a three-body repulsion. So you have to include a new extra parameter to really define your theory consistently starting from unitarity. This means that when you have a unitarity class, you have one constraint that is infinite effect scattering length. You have another constraint that is to go to zero range for the interaction. And then you have a third constraint that is to have a finite three-body energies. And of course, now you want to create a theory for this. And this is very simple because, well, the contact interaction will use contact theories. Contact theories are very nice theory because, well, you have a, the particle becomes elementary degrees of freedom. You don't have a structure, but this is okay because this is universality. So it's not important which is the structure of your particles. And then they can interact only with short range. So essentially, you should not, your physical processes should not be, you should not really care about the structure inside the particles and the long range interaction that you might have in these systems. This put this kind of theories in a very particular spot. They work only for a limited set of energies. But on the other hand, they are very easy to be understood because contact theories are very easy. They have very clear limitation where they work. And as we will see, they are expandable theories. So you can increase the precision of your theory. Of course, they have minimal input required, just a contact theory. And as we see, they are universally transposable, meaning that they work for all the universality class. And now you see how much the pro outnumber the contra. But of course, it's not really like that because, well, when you start to increase the number of particles, or you try to expand more your theory, you get the theory to be more complicated, you increase the number of parameters. So at the end, you have that these theories have some pro and some contra as all the theories, and you don't have really free lunch. But of course, but for sure, one thing that this theory excels in is to make you understand what is the effect of the interaction, because those interactions are very simple to be conceptually understood. So before going to see what is how we can use this theory to understand something about real physics, I want to tell you a little bit about effective field theories because they are important because they connect really the contact concept with the universality class. And they do that in a very beautiful mathematical way. Now, those are the few slides that I have that have some formulas, so I will try to be as painless as possible, as I said. So keep strong and let's dive in this small Lagrange. So this is the Lagrangian of a contact theory. I have the first part is, well, the kinetic part, and then you have this contact interaction that if you prefer the Hamiltonian formalism, this is a contact delta function as a potential. But this is not the only contact interaction that you can write. In fact, if you write derivatives of the contact interaction, you still have contact interactions, meaning that you can have, for example, not only this potential, but you might have also this kind of interaction in which you have your double derivative or more complicated double derivative, fourth derivative, but also you can have, for example, three-body contact interaction, four-body contact interaction, five-body contact interaction, three-body with derivative, four-body with derivative. You have a complete expansion of interactions. And all these interactions come with one coefficient that I call low energy constant, so C2, C11, C4, that in principle should be fixed to your physical system. But this is very good because if you remember from your first year of university linear algebra course, this is actually a complete expansion of any potential with the correct symmetries for your system. Of course, if your system has spin isospin or other degrees of freedom, you have to include it in expansion. But in principle, this expansion, if you take all possible operators, is a complete expansion of any potential. Also, the true potential, if this even makes sense, of nuclear physics. Okay, so just before going on, I will replace all the formulas with Feynman diagrams, so they look a little bit more tameable. but they are actually the same thing. But if I use the Feynman diagrams, everything becomes very nice, and you can picturize this expansion like this. So in this expansion, you have the one-body operators in which, well, you have the mass, the kinetic term, relativistic terms. Then you have the two-body with derivatives and so on. And then you have this infinite expansion of operators. And now, well, this solves the problem, right? So if you don't care about being practical, you just have to include infinite operators and you have solved nuclear physics. But of course, you want to be practical because you cannot include infinite operators in your numerical code. So what is the best thing would be to find a limited amount of these operators that actually contributes much more than the others to your observables, such that you can actually use just a limited subsample of this complete expansion. And actually, this is what effective field theory do. In fact, effective field theories allow you to create a hierarchy of operators, and this is called power counting. In nuclear physics, this is called timeless effective power counting, in which you have a set of orders, and those orders are rearranged hierarchically with respect to an expansion parameter. Here is this gamma, and for effective field theories, I cannot go really into the detail of this, but for effective field theories, this gamma depends on the typical momentum of your system divided by some breaking scale of your theory. For nuclear physics, well, this is the exchange momentum, and this is the breaking scale, which is the pion mass, because here we have only contact interaction, and the breaking scale will be the moment in which you can create long-range interaction. So this expansion parameter for nuclear physics is not extremely small, but it's still smaller than 1, meaning that this series converges. And for each precision you want to reach with your observable, you just need to include a finite number of these operators. If you want to increase the precision, you just include more operators and more orders. The leading order is relatively simple. In fact, you have the kinetic part and you have the two-body, and now you can start to see what is the bivalence with the universality that I described. The two-body, which describe a contact interaction that gives you a very large scattering length. And then you have a three-body interaction. I read the leading order for this power counting. And this takes into account the fact that the three-body system needs to be fixed to some energy. So it's not surprising that even in the theoretical description, you need a three-body that fixes the scale for the theory. And then when you go to subleading order, you increase, well, you get more derivatives and more many-body terms. Okay. Of course, this is not the end of the story because it would have been too simple. But the thing is that you now have a contact interaction, and contact interaction are very, very singular. And if you try to use a contact interaction in your favorite numerical method or in your analytical calculation, you will get observables that are like infinity divided by infinity, and not really useful. So how to deal with this, with delta interaction? Usually, well, what you need to do is to regularize and renormalize the interaction. There are many different ways of doing that. I cannot explain most of them, many because I don't know them and others because I don't have the time. So I will explain a little bit what we do. And we do this, which is the cutoff regularization, because allow us to write from the Lagrangian that we saw before, an Hamiltonian. And to do this, we take the delta function and we replace it with a smeared function of it. So here I use a Gaussian, in which I introduce a mathematical quantity that is the cutoff lambda. This cutoff tells you how close is your interaction to be the contact interaction that you had before. However, when you do this, you are changing your Hamiltonian. And changing your Hamiltonian means that you have a, sorry, there is a question. Oh, sorry. Changing your Hamiltonian means that, well, you have a set of Hamiltonian, one for each different cutoff that you can choose, for which you have to fix your two-body and three-body interaction to your physical system that you want to describe. So for example, if we talk about universality, in which we have a large scattering length, I should fit my C lambda for all the cutoff to reproduce the scattering length that I want. And then d lambda will reproduce the three-body scale that I want for each cutoff. Now, if any observable that I can calculate with this Hamiltonian will not depend anymore on the cutoff when the cutoff goes to infinity. So for example, the observable has a 1 over the cutoff dependence. So it becomes independent when cutoff goes to infinity. The theory is said to be renormalizable, at least at leading order. And I can extrapolate all my observable to the contact limit, so to get back the initial Hamiltonian. Now, one can here talk a little bit more about the fact that for someone, the cutoff takes a more physical meaning. But in all my presentation, my cutoff will go to infinity, so we'll try to reach the contact limit. So instead of talking about that, okay, I want to talk a little bit more about this duality. Now you can see that you have a contact effective field theory in which you have just C0 and D0 to be fitted on the infinite scattering length and to the effective to the three-body system, and then you have the universality. And you see now how those two things are the same thing. However, as we said, the physical systems are not really perfectly in the unitarity limit, and especially the nuclear physics is not exactly at unitarity. How you can do that? Well, this is what the next to leading order of the interaction takes into account. So the leading order will take into account the universal part of your interaction, telling you the most about your physical system, meaning that they will tell you about the emergent phenomena. But then all your observable will be moved in the correct physical position by the next to leading orders. So the leading order is to understand how physics works in qualitative terms, and the next leading order we put the quantitative aspect to your theory. And before going to the physical system, let me give you some examples of universal properties. And the first one is what is called the Efimov effect. The Efimov effect means that when you have a three-body system, and now you fix the three-body scale to something, so you know what is the ground state of the three-body system, and you look back at your three-body system, well, you find out that your three-body system has an excited state. And the energy of the excited state is 22.6 times the square times shallower than the ground state. And then there is another excited state, a second one, 22.6 square times shallower again. And then there is a third, and then a third, up to create tower of excited states in the three-body system that are shallower and shallower up to the threshold. And they are infinite. And this number, 22.6, is this number that keep and continue to return. And this number is universal in the sense that if you fix your three-body system to describe the three-atom system, you will find an excited state with 22.6 universal number, and it will be the same if you use nuclear three-body system or any other three-body system. So these Efimov states are universal and are just a consequence of having universality and unitarity class in your system. And something similar can be seen also in the four-body system, in which the four-body ground state is roughly 4.6 times deeper than the three-body one. And then there is an excitation that is 1.18. There is still, well, some error here because it's a very shallow excitation above the three-body threshold. So this excitation is really close to the threshold, but this number 4.6 and 1.1 are universal number, meaning that again, if you have nuclei, if you have atom or hadrons, you will find again the same numbers. And now you can see how this connects the different fields of physics. And finally, before going really to the physics, let me show you a real calculation. I think this is important because you will see different of these diagrams or these graphics. So it's good that you know what we are talking about before going really there. So this is the binding energy of helium-4 using what is called pionless effective field theory leading order. So you can see, well, the black points are my calculation. They have been done with a few body numerical method. It is a four-body calculation. Inside there is the error band that is hidden in the black dot. And you can see that this energy converges with the cutoff with a behavior that goes like 1 over the cutoff, meaning that I can use this 1 over the cutoff to fit my binding energy to the contact limit, to the infinite cutoff limit. And the result of this extrapolation is this gray band, in which I have the error of extrapolation, but also the error of the numerical method. And you can see how close this extrapolated number is to the experimental data that here is this blue dashed line. So this is an example how I can make this contact theory to work in a real case of nuclear physics. But here I cheated a little bit, because before, in the idea of universality and effective field theory, the leading order of effective field theory is usually the universality class, so infinite scattering length. But when we talk about fineness effective field theory, many times the leading order already contain the scattering length. So in this example, I already fixed the two-body scattering length in spin singlet and spin triplet to the correct value, physical value, meaning that this is actually in the idea of the introduction a next leading order calculation. But many times when we talk about fineness effective field theory as radial leading order, we can take into account the scattering, the finite scattering length effect. Okay, so now this is the new part. So the people that already saw this talk can now wake up. And I'm going to talk about something a little bit strange, because we are talking about hypernuclei. So what are hypernuclei? Hypernuclei are like normal nuclei, but one or more nucleons, neutrons especially, are replaced instead with hyperons. And what are hyperons? Well, they are hadrons, and they carry some strangeness. And in this case, I'm going to talk about lambda hypernuclei. So I'm going to use lambda particles. Lambda particles are spin alpha, 1 alpha particles. They carry no isospin, they have no charge, and they have strangeness -1. So they essentially are some kind of neutrons which have strangeness, no isospin, and they are essentially heavier than neutrons. If I replace one neutron in one nucleus with a lambda particle, what I create is an hyperon. And we have instances, few dozen of instances, in which these single lambda hyperon are bound and stable. And the experimental data that we have for this particle, they are almost exclusively for ground state. We have also some excitation, and we don't have much information for many of them. So there is still room, I would say, to explore this new field of physics. We also find a few instances of double lambda hypernuclei, in which 2 neutrons has been replaced by lambda particle. And for example, we have the very famous Nagara event of helium-6 double lambda, and we have also some instances of beryllium and boron. So it's also possible to create double lambda hypernuclei, but as you can see, there are not many that has been discovered yet. So what is the interesting part of this field? Well, there are many. The first one is that we have a shortage of experimental data, and we would like to know which other experiment we can create and which other hypernuclei we can create in physics. But the problem of a shortage of experimental data already comes in the phase shift of nucleon lambda and lambda-lambda interaction. In fact, we don't have much information about this simple scattering, because it's really difficult to create a lambda particle in laboratory, especially due to the difficulties of have high luminosity in chaotic streams. But okay, the point is that we don't have much phase shift data. Moreover, although we know few of the few body system that you can create with lambda particle, there are many that has never been actually seen in real experiment. And then we have only 3 instances of double lambda hypernuclei, so we don't know how many other hypernuclei there can be out there. But also theoretically, this is a challenge. You have very few data to fix your theory, so you cannot really use realistic interaction with many parameters. And also, even if you can use some kind of interaction, we will see that the theories have some trouble or had some trouble in the past in recreating helium-5 lambda binding energy, so already in the 5 bond. Nevertheless, there is a lot of interest in the field about this kind of hypernuclei. In fact, there are many experiments that has been planned, and there is a lot of movement in the field, and there are still abundant open queries that theories have not answered or don't have an answer, a definitive answer. So it's a very, very interesting field to be studied. But let me go a little bit more in the detail of what is the status of this field. The first thing is the nucleon lambda scattering length. So the scattering length in nucleon lambda has two channels, one in singlet and one in spin triplet. We have an experiment from '68 that tried to fix both of them at the same time. And at my knowledge, this is the only experiment that tried to do these both at the same time. This is the Alexandre et al. Paper. If you want to know a little bit more, there is this nice review to go through and to understand a little bit better what is the story of the history of this field. But even if you have an experiment, just an experimental data that try to fix both scattering singlet and scattering triplet, we don't lack prediction for these two quantities. In fact, different potential, different group in the years try to predict what is the scattering length in this singlet and triplet from, let's say, first principles. And you can see that they are all over the chart. So now you can imagine me try to fixing the scattering length and the two body scattering length in this theory and try to find which one is the best one. And at the end, I realized that, well, I will try everyone. So you will see a few graphics because, well, we try. I will show you only the green one actually in this presentation. But if we go to the double lambda, things get even more complicated. In fact, we have just an idea about what is the scattering length of the double lambda interaction. And we know that it should be something between minus 0.5 and minus 1.9. And there is kind of a story about how this has been developed. And if you are interested, I give you this review in which you can see how this has been calculated, then how there was a paper that said it was calculated not correctly, and then was recalculated. And now this is what we suppose to be true. But also in the theoretical part, there are some problems. In fact, what I'm reporting here is some of the most used interactions for hypernuclei, especially for few and many body hypernuclei. And you can see that, well, I have many different interactions here. And you can see that the system that we know is the hypertriton, the hydrogen 4 lambda, the excited state of hydrogen 4 lambda, we know experimentally. And you can see that if the theoretical interaction can predict well the 3 and 4 body sector, so for example, here, chiral effective field theory A predicts well the 3 body and the 4 body, you have a consistent overbinding of these systems. Now, this is consistent overbinding, except few cases. For example, we have the auxiliary field diffusion Monte Carlo B paper from Leonardo et al. They underbind the 5 body. And then there is the latest chiral effective field theory in which they use a range of different cutoffs. And I was not really sure which cutoff I should use because there is quite a cutoff dependency in the results. So you can see that already in the 5 body, there is still some problem in trying to understand what is why the 5 body separation energy of 1 lambda is what it is experimentally, and there is still something to be studied here, at least, or to be understood theoretically. But what can we do really in practice using, well, universality? The first thing is that we have to realize 2 things. The first one is that the lambda particle is shallowly bound with respect to the nuclear core. So the lambda separation energy is much smaller than the typical nuclear separation energy. For example, in helium-5 lambda, this is a helium-4 plus a lambda particle. The nucleons have an extraction energy of, well, what's 8 MeV. Never when you want to disintegrate everything, so 7, 8 MeV. But the lambda particle is half of that, meaning that for the alpha particle, the typical exchange momentum inside the nucleus is much smaller. But moreover, the lambda particle has no isospin. meaning that you cannot exchange one pion, meaning that the threshold for the pion exchange, so the breaking scale of the theory, is at least the 2 pion. This means that with respect to the nuclear physics interaction, you have an expansion parameter gamma that is much smaller, meaning that the lambda nucleon interaction is much more universal than the physical one. And this means that you can develop a contact theory to write the nucleon lambda and the lambda interaction. Also, the lambda has the same properties. And I will focus on the leading order, essentially because I don't have a lot of data to go over, but also because the error of this expansion will be nevertheless dominated by the nuclear part. So if you want to write this kind of expansion, you have to find all possible contact interaction that describe the nucleon lambda interaction. And you can find 2 different 2-body and 3 different 3-body. And the 3 different 3-bodies set the scale for 3 different 3-body systems, and this becomes very important. And for the double lambda, you have a 1 2-body contact interaction and 1 3-body contact interaction to a final count of 7 new parameter and 7 new interaction to be fitted. And they are just bare enough, small enough number to be fitted on experiments. In fact, these 2 can be fitted on the scattering length in nucleon lambda. Here I can use the hypertritons of the 3-body, and these 2 to the 4-body, so hydrogen 4 lambda and the excited state of hydrogen 4 lambda. And for the lambda, we have the Nagara event, so the helium 6 double lambda, and the scattering length of lambda, even if this, well, there is quite a lot of error in the experiment. And this is what happened if I apply my theory to the most interesting system. The most interesting system in this case is helium 5 lambda, the one that the theories have trouble to describe. And again, you can see that all these different black points are my calculation with some error band. The extrapolation is the gray band, and the experimental result is this blue dashed line. All these graphics represent the separation energy of 1 lambda particle from the hypernucleus with respect to the cutoff that we are using. These different points in the phase in the phase space of scattering length in singlet triplet represent different prediction and experimental data for these A singlet and A triplet. So here we can really compare how the theory, how the contact theory behave when we change one of the input. And you can see that, for example, using the chiral leading order prediction, now this is not the chiral leading order potential, it's just that we are fitting our pionless effective field theory to the chiral leading order prediction for the scattering length. I'm sorry for the confusion if there is any. But using this predicted scattering length, we found an overbinding in what we predict to be the scattering, the binding energy of the 5-body. On the vice versa, on the contrary, if we use Nijmegen prediction, so this other set of scattering length, we find underbinding. While if we use the chiral next to leading order prediction and experimental data that we have, or the mean value for the experimental data because they have some errors as well, we find good consistency with the experiment. And again, this is a leading order calculation, or if you want, if you prefer, from the philosophy of the first slides, this is a next leading order. So we are just including the scattering length. So this tells us 2 things. Well, the first one is that you can define a renormalizable effective field theory, a contact renormalizable effective field theory that describes well 5-body hypernuclei, but also tells you that, at least with the experimental scattering length, you can overcome the overbinding problem. And since we are actually describing by construction the 3-body and the 4-body system, and we are also predicting correctly the 5-body system, we can see how with this very simple contact theory, we can actually describe well this theory. And one might ask why we can do it so good while there are usually troubles. And there is one thing that comes to my mind, and is that actually what we are doing here, we are fixing different 3-body channels. And this is something that is not usually done in the other interactions. So probably this is the reason why this 5-body comes to be good, at least in the using the experimental data. So you can have a clue why some kind of phenomena is what it is in physics, and you can really study what happened when you include different operators. But of course, you should not stop here, and you can go further. And what you can do is, for example, define the same theory by going to the double lambda sector. And in the double lambda sector, there are hypernuclei that we don't know, and we have never measured. One of those is hydrogen 5 double lambda. And you can see here, this is exactly the same kind of graphic in which there is the hydrogen 5 lambda as a comparison. This is using the experimental Alexander et al. Parameterization. And this red band with this black point inside are our prediction for different cutoffs. And the black point is the error of the calculation. And the red one is the error that comes from the fact that you have an error in the scattering length of lambda lambda. You can see that this calculation converges well with the cutoff. So this is good. And we can extrapolate to this gray band. And also that if we change the nucleon lambda interaction to other scattering length, we find very consistent result because, well, the nucleus lambda interaction is actually averaged out in this system, so we don't expect much differences. We can come back to this later if we want. But the point is that try to use our theory for a double lambda, we can actually predict something that has not been experimented yet. In fact, what we find is that this system is consistently bound, even in the contact limit, to have a binding energy of 1.14 plus minus some error band. And we can also estimate the error band of our theory. So this tells you how this contact theory can not only be used to understand something, why some physical systems are what they are, but you can also use them to make a prediction. Of course, the error is still very large. This is because it's a leading order interaction. Well, actually, we have a very large input error. But all this theory is fitted solidly from experimental data. So we really have a theory that is able, for first principle, to predict something in the 5-body system in this case, and that was not experimented yet. And I should say that, well, we have also a calculation in the last 2 years. This is a paper of 2017 that we published, I think, 18. We have a paper from the last year that tried to calculate the same system also in chiral effective field theory using next to leading order. The reference is 2 slides back. And they also find this system to be bound. But of course, there are many other systems, for example, hydrogen 4 double lambda. Unfortunately, for this system, this is just a graphical representation that tells you that, well, using our theory, for some cutoff or some interaction in the, or some points in the parameter space, we find this system to be bound, and for some others is not bound, meaning that we don't have enough resolution or we need more precise data to tell something more about this system. So not all the system we can predict. For example, this one is still uncertain. What we can do is to look at the input parameter space to which input parameter this system is bound, and then we realize that it's bound only for a small portion of these input parameter possibilities, meaning that hydrogen 4 double lambda is probably unbound, but I cannot say much because this is still uncertain inside the error band of my theory, and this is something that I can tell. I should also say that in the same chiral paper, this has been predicted to be unbound. And we did the same exercise for different systems, for example, neutron lambda, neutron lambda lambda, neutron lambda lambda. For the neutral system, there is a lot of debate. And we find that none of them are bound. So just in a nutshell, so if not, I don't have enough time to go to the second part that will require a few minutes more. What we can learn about these hypernuclei. So a part of the interest in hypernuclei, which you might or might not be interested, this was a good example of how I can use universality and contact effective field theory in a real case, especially in a hypernuclei where the expansion parameter of my theory is relatively small. And you can see here that you can, on one hand, understand something about the theory, and on the other hand, to predict something about experiments. So you can really say something and use this theory for understanding something about physics. Okay, I will leave this slide if someone is interested, but it's more about the hypernuclear part. And but I want to focus more on the message about universality. And what I want to talk about now is nuclear systems. And this is more the state of art of our theory and the state of art of contact effective field theories, and what is still missing and what still doesn't work and what we have to work about. Because everything up to now works perfectly. And we're not using this theory for everything if it works. But there are actually some examples in which contact effective field theory shows some shortcoming and we have to be improved. And one of these is nuclear system in P-wave. So do we have, yeah, can you leave me another 10 minutes for this? We started a little bit.
We try just to not go up to 1 hour with the questions. So if you just can maybe to do your last part quick.
Okay, it will not be long. So, okay, so this graphic I don't need to explain. This is the helium-4 binding energy, and you see how good it works. This had no problem. This is what is called S-wave. It's very spherical, it's very nice, few-body system, and was in a very good agreement with experiment. So up to 4 nucleons, contact effective field theory works very well. And now, well, I have to take a step back. I was a student. We did this calculation about helium-4, so everything was working perfectly. And we said, yeah, helium-4 works very good. Why not go into another system? For example, well, instead of 4, 16 particles. Oxygen-16 is a beautiful system. It's spherical, can be calculated with Monte Carlo from microscopical interaction. It works. It looks a very good system. So we did this calculation, and actually what we found out is that oxygen-16 energy is compatible with the 4 alpha threshold. And well, this was problematic. Oxygen-16 is supposed to be bound. So, well, we tried to improve our method. We put more correlation. We made a great optimization method in our Monte Carlo. We did this calculation. We tried to find this bound state. We were even able to find the wave function probability in the space, and we plot it. And what we found is actually that oxygen-16 breaks in 4 alpha. And you see how beautiful this result is in the Monte Carlo, because we never say to oxygen-16 to break, well, all the contrary, but still oxygen-16 break in 4 alphas when the cutoff becomes larger. So this was numerically beautiful, but of course was not as beautiful in the terms of the theory. And well, that was interesting. I was a little bit frustrated about that, but okay, I worked on hypernuclei and everything worked well then. But after a couple of years, I returned back to this problem. And we tried different nuclei. For example, helium-5. And helium-5 break in 1 neutron and a lambda particle. Well, it's not terrible. In physics, this is not unbound. It's not bound. But we tried, for example, lithium-7 and beryllium-8. And they still break in S-wave clusters. And now, if I talk about S-wave, it is in the view of shell model in which I have the S-wave populated, and then I have to populate P-wave or P-shell in my system. And then I have also some result about calcium-40, which breaks in 10 alphas. Now, the question is now, will this kind of system, P-wave system, ever be able to be bound using contact interaction and leading order? And the long story short is no. We tried in our paper of the last year in reproducing the best P-wave system at universality. And when we increase the cutoff to a large value, the system, the many-body system energy, becomes always compatible with the energy of the clusterized system, so the system that breaks, even in the best case scenario. Meaning that when the interaction becomes a S-wave contact interaction, no P-wave or P-shell system are bound. So this was very interesting. Was it the end of the story? No, actually. So we actually saw that the universality class, the unitarity universality class, predicts unbounded p-wave systems, a leading order. But of course, physics is not a universality. It's close, but not exactly to universality. So we can learn something. It looks like that even if physics, microphysics, is that universality, what binds the system, the larger system, is actually the real detail of the interaction. So other correlation that comes next to leading order or subleading order, they should arrive because this is a complete expansion of the theory. So there is the idea, there is the chance that even if a leading order, you don't have a bound system, the next leading order can bind this system. Now, to be able to do that, you have to be able to create a bound state even at leading order. It might be a resonance, it might be something above threshold, but it should be there because the next leading order is much smaller. Therefore, it is just a perturbation to the leading order, meaning that we not create a new pole to be below threshold if you are treating it as in perturbation theory. But what you can do is to move a pole from above threshold to below threshold. But you should be able to create this pole. And this kind of study is something that you want to do. Are you able with S-wave contact theory to create P-wave pole, even not in the physical region, because this is just the leading order, but with the next leading order, you will be able to maybe to move it. So can you move this, can you create this pole in the first step? So the first system, of course, would not be oxygen 16. 16 particles are, well, to study what is a continuum pole in oxygen 16 would be terrible. So you want to stay on the few body system. And the few body that comes in your mind is, for example, 3 neutrons. So the 3 body, but this is not a good system. Well, it's a p-shell system because, well, 3 neutron, at least 1 neutron should be in p-shell because spin and isospin, well, spin. But it's not a good system because you don't have a 3-body system in S-wave that has Efimov effect. So this is not the best system. And in fact, you cannot create p-wave resonances. We saw in 3 neutrons using contact effective field theory. So the system that we are studying are actually a little bit larger. So for example, hydrogen-4 resonance. Hydrogen-4 is the first nuclear system known to have a resonance experimentally. It has actually more than 1 resonance, but 2- resonance and 0- resonance have a natural parity, so we focus more on the 1-. And we know this resonance to be, well, relatively broad, but it's there. And we have also some theory that can predict this resonance. And now our question is, are we able to create this p-wave resonance or this p-wave pole using our theory? And the point is not to really put this resonance in the correct physical position, which we know that is not there, but it should be there a pole. Because if there is a pole in this p-wave system, there is the chance that even oxygen 16 will have a pole. So we try to do this calculation. This is a work in progress. And this is a work that we are going to publish hopefully soon. So if you're interested, stay tuned. And what we found out is that, yes, there is a pole. And this pole is a resonance in this hydrogen-4 system. And this pole converges with the cutoff, meaning that is a stable pole in our system. And this pole, well, it's not really at the physical point. It's actually a sub-threshold resonance, meaning that his energy is lower than the energy of the threshold, meaning that experimentally you could not see the, or it would have, if this pole exists in nature, would have been difficult to measure it in a real experiment. But theoretically, this pole is here, meaning that using subleading contribution, this is possible to be moved back to the physical region. And actually, this pole is not really bad because, well, the imaginary part of the energy is around -3. It's just subthreshold, so would have been here if I have plotted here in this graphic. So it's not very far from the other theoretical prediction. But the important point is that this pole exists. And this pole is a p-wave pole created by a S-wave contact interaction. is the universal point pole that you can create. And then the hope is that you can move, or what you want to test is that you can move this pole to the correct physical region and move it from subthreshold to the normal resonance region. So of course, these are not been done. This is a work for the future to show you that even if these theories are, I would say, very simple and has been studied extensively in the past, there are still questions that can be answered and should be answered. And what you can learn from this theory is valuable. You not only can use this theory for all the systems and all the physics that has little experimental data. So you want to predict something about what is the next experiment you can do, for example, in lambda hypernuclei or hadronic physics. But you can also use this theory, since it's so simple and so well defined, to understand something about why the physical system are what it is, how the different three-body contribution contribute in million-5 lambda, and what are actually the detail of the interaction that makes the p wave or p shell nuclei to be bound. This is something that we have not achieved yet. We don't have bound nuclei, but the hope is that increasing the order of the interaction, you can actually start from an oxygen cysteine which is unbound and revert Lorenzo CONTESSI PhD and return to a bound oxygen cysteine. And okay, let me just finish here. This is just a final resume of everything. What we saw, what I show you today are two systems: hypernuclear physics, hypernuclear system, single lambda hypernuclei, in which you can see a contact theory which has small errors. And you can use this theory not only to overcome the overbinding problem, but you can predict double lambda hypernuclei, and everything works well. So hypernuclei are very nice because the lambda particle is a different kind of fermion than the nucleon. So they are always in S wave with respect to the nuclear core, meaning that you never have p shell problems. And in the other side, we have nuclear physics, when we can actually use contact effective field theory to understand a lot about the physics that we are talking about. But still, we have some challenges to be faced in the future, for which this kind of theory need work, and for which we are working on that. All these two systems, well, together with hadronic physics and atomic physics, are connected by the idea of universality, for which the same theory and the same thing that you learn from one system can be applied to the others. And how to apply universality is by the using of contact effective field theory. And now you can see how all these systems come together and how you can pass from one to the other using this simple concept. And this is the end. Thank you for your attention.